Okay.
Okay.
Yeah, is it recording?
Yes.
Yeah, okay. So this is problem H. Basically, you're given a tree, and each node you can assign to two basically like two IDs. And in order to connect two nodes, you want to like have them share one or two IDs. That's like basically the gist of it. So you're given like a graph, and then each node you can assign to two numbers to it. You want to use up as many numbers as possible, such that like using up a number means that at least two nodes that are next to each other share that share that ID.
And it's a tree.
Yes, it's a tree. So that makes it really, really easy. Yes. Okay. So, yeah, so basically I'm just gonna, like we have a good tree basically. And we can assign like two numbers to each one. And then if we want two of them to be connected, then they should if we want them to share an ID. So like if this is like 1, 2, then we might connect these two with 1, and then this could be like 1, 3 or something, and so on. And so here, like number 1 would be used. And given a tree, we want to assign numbers such that the maximum amount of numbers is used on any edge, basically. Okay, so the way to do this is basically, it's a pretty simple DFS, actually. We consider a case where let's just say we take a look at this node, and suppose that we let like 1 be the neighbor to it, that like the node leading into it. So obviously 1 has to be at one of the, what is it called? 1 has to be the ID here. In order to make this connection a 1. And then we have different choices on how to assign this other value. So the way that I thought about it was that if it can connect to more nodes, then we can use up more IDs. So let's just say that if this can connect to more nodes here, let me just erase this here, then we can assign this ID 3, for example, and then we can use this 3 later on to create more connections with this number. And on the other case, if it doesn't have any children, if that node doesn't have any children, 1, 2, like this, then the best case would then just be to assign this to the other one, like this, so that we get 2 connections on like the same edge, basically. And that's basically like how you do it. Basically, you just keep assigning down new IDs as long as the node has children. Otherwise, just look at the parent and then make it the same.
So you start by giving 2 numbers to the root, and then just greedily assign the value to the children. And,
yes.
Okay.
And this just works because each node can only ever have can only ever use 2 numbers. So if we have 1 number for like going in and the second number for everything going out, that's the most it can do anyways. And for like the root node here, we have to there's like another special case because you have to make sure that this also has 2 numbers going out. So you assign the first one to the first child, and then the second one to every subsequent child. But yeah, that's like the basic idea. It wasn't that hard of a question, so I didn't worry too hard about it.
Okay.
And yeah, we're skipping J, and those are the only 2 that I did.
Okay.
I think we saw C before in like a previous.
Yeah, CP2 we used it before. Yeah.
Yeah. But Trung solved it, and yeah, it doesn't really matter.
Okay.
I want to go last because
Okay.
I have like the hardest ones. Trung, you go next.
Trung, you want to?
Yeah, sure. So I solved T and I accept from C, of course. So the problem is like, so to put it simply, you have a DAG, where each node except one node, which we will call the end node, each node has exactly two out edges. One is called the left edge and one is called the right edge. So there's a process you will repeat like n times. So the process is that you put a ball, you put a ball you put a ball at node 1. So the end node is node 0, but that doesn't really matter. So you put a ball at node 1. So whenever a ball reach a node, it will go through like the edge that the node is currently pointing to. So like previously we know that each node has two edges, and we also know that like at each moment in time, which edge is the priority. So like, yeah, at each time there's either a left priority or a right priority. So whenever a ball reaches a node, it will go through the edge, the priority edge, and then it will also simultaneously like toggle the priority edge, like from right to left and from left to right of that node. And the ball just keep going until it hits like the end node. And yeah, we repeat the process n times. And at the end, we need to know like what is the state of each node, which priority edge it is having. Yes. So there are 500,000 nodes. Repeat the process 10 to the 18 time. Okay, so let's draw. So the first thing you notice is that because it's a DAG, there's like each like at each moment after a process, the ball will always go to the end node. So let's first try to topo sort like the graph, and we will see what happens. Something like this. Oh yeah, and the left edge and the right edge can maybe point to the same node, but that's like not a really big detail. So suppose we start here. So I will claim that from node 1, if we know like the state for node 1, if we know like the state, the original state of node 1, suppose like it goes to the left, and we know the state of node 1, and if we also know like the number of operations, the number of times the ball touches node 1, which is basically the number of operations we need, because like every operation we touch node 1. So I claim that if we know the initial state of node 1, and we also know the number of times the ball touches node 1, then we know how many times the ball will go to the left edge and how many times the ball will go to the right edge. That is because like each operation, the ball will toggle like each time like the ball touches node 1, it will toggle the edge, and it will go like it will flow through an edge, and it will also toggle the priority. So we can just kind of like simulate, because it just toggles left right, and so we can know like how many times the ball will use the left edge and how many times the ball will use the right edge. So yeah, does that make sense?
So I guess it's not exactly simulating, right? You're just counting, right? So
yes. Yeah.
Yeah.
So now we know like for node 1, how many times it will go through the left edge and how many times it will go through the right edge. We will know like how many times the ball will touch the left node and how many times the ball will touch the right node. And then we just repeat this process for these two nodes. And yeah, so like my solution is to tuple sort and then repeat the process. Yeah, that's D.
Okay.
Okay. So, okay. So let's move on to I. Where is it? So I is like so you have a complete graph where there's like 14 nodes, and you want to know if like there's a Hamiltonian cycle of weights exactly L, where L is given. This graph is like connected, and yeah, I think undirected and weighted. It's an undirected, weighted, complete graph. And you want to know if there's a Hamiltonian cycle, which means a cycle that goes through every node exactly once, which has the weight equals to L. So N here is 14. So I don't know why, but yesterday, while I was like starting on the problem, I keep thinking about like meet in the middle, but somehow I did not like get the idea until I like think of it like a different way. So I'll talk about why I struggled on it earlier and then what I did. So my initial idea was like split because n's like 14, and obviously you cannot just binary like brute force 13 factorial. My idea was first to split like the set of nodes except one, because we know it's a cycle. Let's just say that like the cycle starts at 1. It doesn't really matter if it starts at another node. So my first idea was to split the ladder nodes into 2 halves, and then try to find like maybe a cycle on this part and a cycle on this part or some sort like that. But it turns out that this is not like really easy, because it is not very trivial how to merge the 2 parts together. Like a trivial, like not a trivial, but an important part of meet in the middle is to merge the answer of 2 parts together. And it is not like easy in this case. So what I did was to think of it like the other way. So we have a cycle of 14 nodes. And let's say we start at 1. So what if instead of a cycle, we consider 2 paths that has length of 7. So let's say this is node U. What about we have 2 paths of length of 7? So this is better. This is better. You can't brute force this. So what now like my idea was to first brute force every path that has length of 7, and then after that I just like I maintain the information of all of these paths, like which nodes they use, which can be maintained using bitmask, and also which like the path starts at 1 and where does it end. So yeah, so like my information contains each path contains 2 information, the bitmask of the nodes that is used and the end node. And then now what I did was to basically brute force again, but then now I need to merge like 2 paths together, right? So for each path where I brute force again, where there's an end node and a bitmask, I check if there exists like another path which the same end node, but like the complement of the bitmask, which means that it uses the other nodes that is not used in this path. So I brute force again, and I check if there's like another mask with like the suitable length, which can be added to the current path to make like length exactly L. And then, yeah, that's just my solution. I put everything into a vector and then sort them, but I guess there's some other ways like putting into a map or something.
So you consider all length 7 paths?
Yes.
And how many are
there? So for each length 7, there's like 14, actually 16 choose 6 because we have fixed a node 1. 16 choose 6 nodes.
You fix the first node.
Yes. And then for each of the
you mean 13
nodes,
choose 6, right?
13 choose 6, and then you order the next 6 nodes,
so that's,
which is actually not too large. I think it's about 13 million. Yeah, so I brute force this and then I save. I store all of these 13 million maps in like in like a map with these informations associated with it, and then I again brute force these 13 million paths. But now, like for each path, I only have to check. I don't have to brute force the other half again. So I just like take the information from what I stored in the map.
So the goal is to have exactly L, right?
Yes, exactly L.
So then I guess similar, after you do, you can also just sort all the value and use 2-pointer. And if you find the 2 value sum up to L, you see whether the bit mask are totally complementary. That should also work, right?
Yeah, that should work too. Okay. I don't have to brute force again. That's true. Okay. Cool. Yeah, so that's all of my problems.
Yeah, I guess this I guess this my first I guess the first I saw number 14, I was wondering whether there's something using bit mask the DP kind of converted into 2 to the n times n or something. But I guess for this because the path is order matters, so actually you cannot reduce the sub problem on a subset using just a subset. The order actually matters. You don't get reduced number of states that
well,
way.
Actually, you can do bitmask DP. It's just because like the path is like 10 to 15, so you cannot store like the other dimension at all.
Okay. So if L is small, then you can do DP. Yeah. Because but I guess in general, this meet in the middle fairly generic in this kind of like NP complete problem, so that you can solve are there, well, I guess are there is there all kind of NP complete problem, can it always be applied, or there are cases where it cannot?
I actually don't know. Okay. It's like just some way that you can think about the problem.
Okay.
Okay, that's all of what I solved.
Ready? You're muted. Yeah.
He's not talking. I think he's just wait for
he needs to start talking at some point.
Sorry, the window froze for me. Okay, it's back. I'll share. Okay, you can see.
Yeah.
Let's see. Okay, I'll start with like I think F is actually the easiest.
Yeah.
Yeah. Okay, so in this problem we have a bunch of points in the plane, and we want to know if it's possible to find a line that has a certain like number of the points. So specifically what it is like we have n points, and we have some integer p, and we want to find a line that contains p% of the points all on that line. So we just need to say if it's possible or impossible to find such a line. Now, the number p is actually pretty big. So like greater than or equal to 20%. So that means like if it's possible, then there should be a lot of collinear points. So then the idea is if there's a lot of points on the same line, then if we pick 2 at random, we actually have like the probability of them both being on the desired line is like would be about probability like okay, well, it's p over 100, I guess. But whatever the probability that is on the line, it would be that squared. So this would be greater than or equal to like 1/25. So if we pick 2 points at random, we have a pretty good chance that we found it. Wait, did I do this right?
Yeah, I think that's correct.
So what we can do is can keep random, like we can take a bunch of samples of pairs. Like let's say we do it like t times. So then what's the probability that they all fail? It would be 1 minus 1/25. And they would have to fail every single time. So like to the power of t. So if you do it like, I think I did it like 100 times or 200 times or something like that, then this is actually a very small number, like it decreases exponentially. And so this one probability is already not so close to 1 that, or it's not so close to 1, so this exponential like decreases very fast. So yeah, essentially the solution is you pick 2 random points like a bunch of times, and then to check if it's a solution that satisfies the condition, then we just check for every point, is it on the line? And then to check if it's on the line is like you can just do a cross product.
Oh, cool. Yeah, I guess this is my first time seeing a CP problem that use a randomized algorithm. I guess there must that been, I guess, in large part due to I haven't seen many, but even just in the practice, this is the first time we actually use a randomized algorithm. It's nice.
It's not very common, but it does randomization does appear.
Yeah, and it's.
Okay, then the next one would be E, which has an intimidating title and like lots of formulas and whatever, but it's actually pretty simple. Yeah. So, like it tries to scare you with like with an impossible problem, basically, or with a hard problem. Actually made this one. Okay, so this problem says, in order to like, so TSP is like you want to visit every city exactly once and to like minimize the total trip length. So it's like a famous hard problem. But we're not actually asked to do that. Instead, what they're saying is that there's an approximation algorithm that takes a certain amount of time to run. So let's say we want, let's say we want a solution to be like within c times the optimal solution, or what exactly was it? Essentially, it's like running you want to run an algorithm to find like a path, and then you take that path. So then like those 2 actions combined give you a total amount of time. And the question is like, what's the optimal like parameter to minimize like that total time. So it's like running the algorithm takes this crazy function where c is the only like unknown, everything else is known in the input, and then the amount of time it takes to like take the cycle that it gives you is this amount of time. So basically, we just have like this crazy function that we want to minimize, like across all C. We want to find the optimal C. And then what I did was, like, you can say, if you want to minimize it, you can take the derivative and set it to 0. So I did that, and then it was something like I don't want to work it all exactly because it's kind of just constants everywhere. But essentially, you get something of the form like there's some constant A times C squared times E to another constant times C equals, like, say equals 1. So I get something of this form for like some constants A and B when I take the derivative and set it to 0. So this function is like always increasing with C. So like a C goes to, when C is 0, the left hand side is 0, and then it's increasing like to infinity. And we want to find where it's 1. So then for this, you can use bisection. So like at this point, it's below this line, and then you can find some point here where it's above the line, and then you can check the midpoint, and so on. So in like log-n steps, you can find a point where it's equal to 1, or where it's where it's within a certain precision of such a point, and that's pretty much it. So you just have to take this formula, set the derivative to 0, and then binary search.
So I did it the slightly different way. So so basically without using math. So essentially the function we're trying to minimize is the sum of two functions. One of them is monotonically decreasing. One of them is monotonically increasing. So their sum will be this concave shape. So we're trying to find the minimum value in this function. So then I did the trisection to find it. So and so basically, given the range, you evaluate at 1/3 and 2/3 of the range, and whichever one, if you find one value is bigger, then you can throw away that 1/3 part, the bigger that outside the bigger part of 1/3. So then that turns out to also work.
Yeah, so that's called like ternary search. So like if we have some range L to R, then we try like we split it in thirds. Whichever side is bigger, then we throw out that third. Yeah. This actually appeared in like 2 other problems in this contest.
B, I guess.
I guess for this one, it wasn't clear to me that you could.
Yeah, I made there was a leap of faith that it's a concave.
Like I think, like an increasing function plus decreasing function, I think is not always unimodal. So I don't know.
Really? Actually, I guess in the my research, actually a lot of time we actually have this kind of optimization problem when we are choosing some parameters. So then there are 2 kind of error. One of them coming from you have to add noise to make data private. The other coming from you are basically releasing more coarse grained information. So then the optimization is true. But a lot of time we don't know the exact constants of the two functions. So then it can't be directly optimized.
Actually, I might want to. I'll check that later.
Okay.
Increasing plus decreasing is unimodal, but I think I remember it's not. I could be wrong. Let's see what's next. Maybe K. So in this problem, we have like this cycle of luggage that's like length L. So then you're standing, so like luggage is moving around the cycle at like a constant speed. and you're standing at some point, and then if a piece of luggage is in front of you, you're able to take it and put it on your cart, and it takes like a fixed amount of time to put it on your cart. So like after it's on your cart, then you're ready to like pick up another bag, but you can't like pick up 2 bags within that amount of time. So the question is, like, we want to know 3 pieces of information. So like we don't know like where you start, like maybe you're standing here instead. So what the question asks is like what if you stand in the best possible spot, what's the amount of time it'll take you to load bags? And then the other question is, what's the maximum amount of time it could take you? Like if you stand in the worst possible spot and like unload them the fastest, then how long does that take? And then the other one is like, what's the average of like all starting points? And they want it in a fraction. So the first observation is like, it's always best to take the bag, like the next bag that you're able to pick up. Like there's no reason to let a bag pass you, because then that will just like that'll just make you unavailable. Like if I waited for this bag, then I would just be unavailable for like more time instead. So
I think the problem specification said you always take the next, so there's you don't try to optimize.
Well, anyway, if they didn't say that, then you would always want to take the best anyway. Okay. So you always want to take the next one. So another thing is that the constraints are somewhat small. So like we can afford, in theory, we can afford to try every starting location. Well, not everyone, but we can try like enough. We can try n starting locations, and then for each one we can check how long it takes, like by simulating. So like the actual number of positions is like 10 to the 7, so that's too large. But like starting here and starting here are pretty similar. Like the only difference is like that initial waiting time for like the first bag. So if you just try like between each position where there's bags, you just try those, or like you just try starting at where a bag is. You can only it's enough to just try those as your starting positions. And then so to simulate it, what I did was I have like a set containing all the positions of the bags. To simplify the process, I'm thinking that instead of like the conveyor belt moving, say, one direction, you're actually moving the other direction. That way the set of like bags is always like the same positions. So it's like, let's suppose that I stand here, I pick up this bag, then the next time I'm available is over here. So then I can binary search like in my set, or I can find the lower bound in my set for like when the next bag is. And then I need to wait another amount of time, and so on. And then I remove things from my set n times. So like so in the simulation process, I try n starting locations, and then it takes n operations of like removing a bag and finding the next bag, and then each operation takes like log n time to find where the next bag is. So that's how long the simulation part takes, which is enough. So then to answer the questions, the minimum time is, it's always best to start where a bag is. So we already have that right now. Like there's no reason to wait for the initial bag if we're trying to minimize. Then for maximum time, then we want to wait as long as possible for that first bag. So we should actually so we still have enough information. We just say, to measure the starting point, we just say, what if we started like right here instead? So then we have to wait all of this time for this bag. So we can compute, so from the answers for the minimum amount of time, like if we start at each point, then we just make them start as far as possible, but not so far that they're in front of the other bag. One edge case to think about is like if all of the bags are in one position. I don't know if they guaranteed they're not or something, but I handled it. So like if all the bags are in one position, then you might calculate like the distance to the previous bag is 0 every time, but you should consider like, what if I start here and have to wait it to make it like an entire cycle? So that's one edge case to consider. Okay, so then the only remaining case is like finding the average, and that's pretty similar. Like you just say, for this bag, if the earliest possible starting position is here, it's like we have to take the sum of all of these times. So like let's say if we start exactly here, it's t, then over here we have t plus 1, t plus 2, and so on. So essentially we have like sum of time plus I for I equals 0 to like distance minus 1. And then it's just simple math. You can do like td plus d minus 1 d over 2. And if you have the sum of all times, then you just divide the whole thing by s. And to get it as an irreducible fraction, you just take it. You just divide both by the GCD.
So just to confirm, so you use a multi-set during simulation, right? So.
Yeah. So in the simulation, there's like multiple bags in the same position potentially. So I use like in C++, the class multiset is actually kind of annoying to use sometimes, because like to erase an element, it will erase all copies, so you have to like erase find. And I think multiset.count is actually pretty slow. I think it's not login.
So what do you use? What did you use?
Instead I use map.
You use a map, okay.
So it's like, given a position, it'll tell me the number of bags in that position. And then if the number goes to 0, then I erase that position from the map.
So yeah, so I was burned by multiset erase all occurrence of element once. So I will remember that for a while.
I don't know the last time I used multiset, because like you can usually just use map.
Right. So Trung, is that your recommendation as well? So do you use multiset at all, or do you also use map?
I don't have like
if you were to do it, would you use multiset or do you use a map?
I'll use a map.
You use a map. Oh, okay.
Like multiset map is like multiset, but it has.
Yeah, I know it provides same fun, but just because in Java that's what you do. You use tree map if you want to duplicate. But C++ doesn't have it. So I actually, this is the first time I heard to avoid the multiset. So just want to check.
So yeah, I've been annoyed by multiset plenty of times, that I just use map a lot. I think next problem is G. So, okay, so in this problem, we have several people at different positions, and they move like Manhattan distance. So like you can only move like left, right, up, and down. Like that's their walking distance. The question is, we want to choose a point. I think it has to be integer coordinates too, because it's like it's describing a point by like an intersection between like a street and a road. So we want to find a point like an intersection where all these people should meet. And so there's two requirements. So the first requirement is that every person should be able to walk like everyone should be able to walk at most distance d. So it says like we have this integer d. So we should make sure that no person has to walk more than d to get to this intersection. So that's the first requirement. And then the second requirement is among all possible intersections where they can travel like at most d, you want to choose the one where the total distance walked is minimized. Okay. So the first thing I thought was, what if there's no requirement? Like, what if we just want to know, like, what if there's no requirement about d? So, like, what if we just want to know, given a point, what's the total distance? And the answer is like, it would be the total, it would be the sum of distances for x plus the distances for y, right? And if there's only distances for x, it's actually known that the optimal point is whatever the median is. So like if there's an odd number of points, like then this is the best intersection. This is the best intersection for x. If there's an even number, then anything in like the range between the middle two is best. And more specifically, it's known that like if you say a function of where the starting point is, or where the center intersection you make them all meet at, wherever it is, if you plot it like as a function of what's the total distance, it will be like a convex function. You can maybe think of it like you're taking the sum of all of these absolute values. And the sum of convex functions is convex.
Yeah, so I guess these, I think the standard observation is when you are optimizing this for Manhattan distance, then the choice of x and y are independent from each other, so you can optimize them separately.
Yeah, so that's what I was thinking.
Yeah, that's what you alluded to earlier. So I just want to, because for people who are not familiar, that's yeah, it's an important insight.
Yeah. So like that's what I was saying earlier. Like it's just the sum of the x distances and the sum of the y different distances. So those are completely independent. Now all of this so far has been about like if there's no requirement about d. But yeah, so if there's no requirement about d, then the solution is to take any intersection that's like median of x's and median of y's, and then that would be the solution. But unfortunately, that's not necessarily within d of all points, even if there is a point that's within all, like within distance d to each person. So I had to like, okay, now we had to think about what's the actual solution space that people are allowed to meet at. So let's say we have a point, we have a person here. Then consider all points within distance d. That would be like this diamond. Like this point would be like x minus d y. This would be like x y plus d and so on. So for each person, like the intersection that they meet at must be within a certain like diamond of that person. So the intersection of all of these diamonds is like the set of points where they're allowed to meet to satisfy the requirement. So how can we compute this, or how can we compute and represent this set of points that they can all meet? So what I do is, say we have this point like in the diamond I'll represent the diamond by like 4 conditions. So these 2 lines give a bound on x minus y. So like there's this interval where the value x minus y must lie between. And then these 2 lines give a bound on what the sum can be. So what I do is, like if we consider x minus y and x plus y separately, then among all the points, we have like a bunch of intervals here, and we have a bunch of intervals here. And then to take an intersection of intervals, we take like the maximum L and the minimum R. So in the end, the intersection is like, is like we have like these conditions. Okay. Now if we picked like 2 values within these intervals, then it's not necessarily an integer point. So like if I say a equals x plus y, or a equals x minus y and b equals x plus y, then this gives us, like if we add up these 2, then we get 2x equals a plus b. And if we subtract them, then we get 2y equals b minus a. So like it would be like a half integer, potentially. It depends on like whether a and b agree on sign or something. So it's something to be careful of, and like it requires us to make it an integer. So that's something to be careful of. But okay, so that's just an implementation detail, but conceptually, like we have some like diamond rectangle thing in the plane, and we want to optimize the total distances in this region. So then here I remembered that the function of total distance is like for one of the dimensions x or y, it's convex. So it also means that like the function, it will be like it'll be like f of x and y, like where we choose the point. This function is convex. So we have to optimize a convex function over this diamond shape. So then at this point, what I did was, let's say we fix what row it's in. If we want to optimize a convex function, we can do that in log n time with ternary search, as was described earlier. Like, so given a row, we can find what the minimum value is in log n time, and then I just do it again. So like, a ternary search, which row gives the best solution. It's like, so it's like a nested ternary search. It's like given an interval, like split in the middle, I find like what the range is intersecting with this diamond shape. I find the minimum, and then in another row I find the minimum, and then depending on which one's larger, then I cut out like this. Then I cut out like this strip, and then continue ternary searching on this interval. So overall, the solution is like n log squared, because I do log n ternary searches, which is each one takes log n time. So is the solution clear?
Yeah.
So then now we move on to A and B. I guess we'll start with B. So in problem B, we have some map, which is given by a rectangle. We have a starting point A, an end point B, and there's several bike renting places, or like bike stations, they say, represented as like points inside the rectangle. And they also say any point on the border of the rectangle is also a bike station. Okay, so how do we move from A to B? So like we're person A, we have a certain walking speed and a certain biking speed. So we don't have a bike, but what we can do is like we can walk around at our walking speed. We can pick up a bike at any of the bike stations. Then we can ride around at our biking speed. But we can't just meet point B. We have to drop off the bike. So maybe like we could drop off the bike here, then we could walk to another bike station. We could bike again. Any point on the border is also a bike station, so then we can return it here and then go at our walking speed and meet point B. So like that's the kind of thing you're allowed to do for like a valid path. So you can only move at the biking speed if you have a bike, and you have to pick up a bike to use it, and you have to drop off a bike before you meet the person at the end. The constraints are like there are 1,000 bike stations. So the main observation is that it's never useful to pick up a bike twice. So like it's never useful to pick up a bike, drop it off, pick up another one, drop it off, then meet the person. Because it would always be better to just take the straight path to like the last point that we drop off the bike, assuming the bike is faster. And if the bike's not faster, then we just take a straight line anyway. So then there's just several cases basically. So first, maybe it's best to just walk in a straight path to the destination, or maybe we should pick up a bike at one of these points, drop it off at another one of these points, then meet the person. And if that's the case, we can brute force over all pairs of points. There's only 1,000 of them, so we can handle all those cases as well. So then the only tricky parts have to do with the boundary. So it could be that we pick up a bike, drop it off somewhere on the boundary, then meet the person. Or it could be that we go to the boundary, then drop it off at a point, then go to the destination. Or it could be that we hit the boundary, then we hit the other boundary, or hit another boundary at some other point, then we meet the person. So there's like 3 separate cases where you could use the boundary. Yeah, so there might be like a math solution to this, but in this case, I just kind of checked that all of these cases, or I kind of guessed that all of these cases are also like ternary searchable. So like we can iterate for every point and for every segment. Let's say we fix a segment. And let's say we're starting with A. Then we should hit this segment and we fix some point like this one. And then we should go to point B. So that function of like what's that total distance is a function of like which point on this segment do we choose. So it's like a function of just one real number. So I just ternary searched on where it is for like some fixed number of iterations. I did like 100 maybe. So like I ternary search, evaluate the distance, use that to determine like which interval we're in. So yeah, we ternary search to find a point. And then we just handle all the cases like that. Like maybe we hit this point, then we go to here, and then B, and then we just ternary search on where the point T is. So now the only other case is if we hit like 2 boundaries. So then for that case, I fix 2 segments. So like I try all pairs of like boundary segments. And then if we fix two pairs, then I also binary search, or I also like do a nested ternary search. So like a ternary search, what's the optimal point on this segment? And then if we fix a point in a segment, then I find the optimal point in the other segment with another ternary search. So I didn't really prove that this is optimal, but it seems like it would, it seems like it would be ternary searchable because like distances. I know like distance is convex, but hopefully like these sum of distances will also be convex in just the right way. Yeah, it's pretty similar to like G, I guess, in some ways.
Lots of ternary research.
Yeah, three problems with it. Okay, then the last problem is A, which I thought was actually pretty interesting, but it's pretty hard. So, okay, so in problem A, we have, two polygons. One is inside of the other and they don't intersect. So it's something like this. So like we have polygon A and we have polygon B on the outside. So the question asks, like the region in between these two polygons is like a racetrack. And we want to know what's the shortest possible loop that contains the polygon A and is contained in the polygon B. It's like what's the shortest possible race trip, I guess. And note that it's not just like the perimeter of A, because like that would be a valid path, but it's not optimal because like, you know, we can take shortcuts. We don't need to like go inside. But like connecting any 2 points of A might intersect with the boundary of B. So it's also not just the convex hull of A. So we have to find, the shortest possible time. Or shortest distance cycle. And the constraint is like n less than or equal to 50 for both polygons. So I thought of several things for this problem. Because the constraints are small, we can afford to do things like we can check for any 2 points if we can like take a path between them without intersecting, like without violating the rules. Like we can check this segment is not allowed because it's inside of A. We can check like the midpoint is inside of A. Point and polygon is like a library check you can do. You can also check something like this is not allowed because it intersects an edge of A. So you can check segment intersection to check if if going straight between 2 points is valid. So that's one of the first things to think about is like we can check for every pair of points whether we can travel between them in a straight line. But the issue is what was hard to think about is how do we distinguish a cycle in this graph from how do we distinguish whether it takes a trip around the center polygon or just say it just went here, 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 right? Like we shouldn't call that a racetrack because it didn't go around this. It didn't go around the whole track. So that's really the hard part of this problem, to think about what does it mean really to go around A, and how do we encode that to get like a shortest path problem.
So without the B constraint, it's just convex hull, right?
Yeah, if there was no B polygon, it's convex hull.
So then if you convex hull one edge of convex hull intersect with the B, should you just go to the first point on B? So instead of following your path to intersect, you go to the next point that intersection, and then you try to go from there to the next point. If it's again intersect with B, then you go to that point. Would that be correct?
I think in general, like it can intersect B in lots of strange ways that it seems clear to me that that wasn't the right path.
Okay.
I don't know if I can think of an example right now, but
so it's just could go wrong. Yeah.
Like you can think that they could like wrap around each other in really strange ways. Yeah, that's it. Okay. Like let's say this was our polygon. Like let's say this was A. We might imagine B does something strange. Right?
Okay.
So like it's not obvious to me, like
I see.
Yeah, they could just intersect in really strange ways, wrap around each other, and it's not obvious like if it's not as simple as like it intersects at like a point and then we visit that point. Okay, so let's say we have all these edges, but we really need to think how do we decide whether a cycle actually goes around A? And so one thing to think about is, well, first of all, to make it the shortest path, like we want to know where to start, and there's no like starting point in this diagram. One thing I said was like, okay, let's say we pick the leftmost point of A. It's always best, like there's always a best solution, an optimal solution where we do visit this point, because like if we were more to the left, then we could than the leftmost point, then we could like, I guess you can think like you never need to go like further to the left because you can like straighten it out, I guess. I guess it's not a proof, but let's assume that a path, there will be an optimal path that takes like the leftmost point as some, let's say as a starting point. So one thing to think about is like, how do we distinguish like a path that just goes back to itself without going around A? So one thing I thought about is like, what if we set a checkpoint like somewhere in the racetrack, right? Like if we have a checkpoint here, then it has to visit the checkpoint. So it has to travel like that distance around it. In theory, we want it to like go around the other way, but at the same time, like how do we make sure it doesn't just go back around the same way it started? And so it's actually kind of hard. So what I did was, like, let's say we take the rightmost point. And what I did was I extend array from this. Maybe I'll color it in like red. I extend array from the rightmost point. And for every edge that crosses this ray, like let's say this edge here, if it crosses it going right, like if it crosses the ray from the left side of the ray to the right side of the ray, we can keep track of that. And then it can't go around the other way because then like we'll also keep track of that. So how I actually encode this in the graph is like each node has two versions. So like if this is like a point U, then I'll say like there's U0 and U1. So I say that U0 means that I'm at the point U and I haven't crossed this ray counterclockwise yet. And then U1 says I've crossed the ray counterclockwise once. And also there's so yeah, that's basically what I do. Like we want to find, overall, we want to find a path. Like if this is node S, then I'll say like we want to find a path from S0 to S1. So most segments, like if a segment doesn't cross the ray, then I'll say it connects like it connects V0 to V0, and it connects V1 to V1. So like if it doesn't cross the ray, then nothing changes. And if it does cross the ray, then I'll say like this edge would be from like U0 to V1, like between those two. So that's essentially how I keep track of whether I've actually like been around the polygon. So let's see like why something can't cross the ray then come back. Let's say A is like some simple polygon. What if B is like really complicated and zigzaggy? So I have the ray like going this way. Okay, so if I take a path here, I'm like I'm in like a 0 node, then I travel to a 1 node, then it would be a 0 node if I tried to come back. Then it would be a 1 node, 0 node, 1 node, 0 node, 1 node, etc. So even if it's more complicated like this, say like if it's necessary to cross the ray and back many times for a solution, which might happen. I guess this isn't really an example of that, but like if A and B are both kind of
both twist and turn.
But basically any path, like we'll consider whether it crossed in one direction more than it crossed in the other direction. So it's like it'll be valid like in actually distinguishing whether a path goes around. And this is extending a ray from a point and checking like how many times something crosses the ray. That's actually like the algorithm for checking if a point is inside of a polygon. So like you can think of it like the polygon A. To check, like you can think about the path that it takes. We can think about distinguishing it about whether it contains like the rightmost point. So like it has an analogy to that algorithm. It's like if something didn't contain the point, then it doesn't contain A. And if something contains the point and doesn't cross A at all, then it contains the whole polygon. So really it's about like encoding that point and polygon algorithm inside like shortest path kind of. So I thought this problem was pretty interesting. It's pretty hard to get it right.
Cool. You have to go around the Cape of Good Hope because the Suez Canal is blocked.
What was that?
Oh yeah, we're just saying you have to. You are checking. You have to go around that corner. So I said you have to go around the Cape of Good Hope because the Suez Canal is blocked. Are you guys following the news at all?
Yeah, I heard about that.
Yeah. Okay, cool. Yeah. So I guess that's the last problem.
Yeah.
Okay. Well. Thank you.
Thank you.
Thank you, guys.
Thank you, guys.